Welcome back, everybody. Today, we're going to be taking a deep dive into this paper called Hemispherical Power Asymmetry, Anomaly in the Cosmic Microwave Background.
Oh, cool.
Yeah, it's all about this really interesting anomaly in the universe's first light, you know,
Right.
cosmic microwave background,
Right.
or CMB, as I'm sure most of our listeners are familiar with. You can kind of think of the CMB as like a baby picture of the universe.
Yeah.
And it turns out this picture might be showing us something we weren't quite expecting.
Yeah, that's right. This baby picture is kind of revealing what scientists are calling hemispherical power asymmetry,
Okay.
which is a pretty intriguing find that's raising some pretty fundamental questions about the universe.
Okay. Hemispherical power asymmetry, that's a mouthful.
It is.
For those of us who you know aren't cosmologists,
Yeah.
could you break that down a little bit?
Sure. So imagine you're looking at a map of the early universe.
Yeah.
It's seen in the CMB.
Yep.
Okay, so now split that map down the middle.
Okay.
What we're finding is that one side of the map shows way more temperature variations than the other. Like
Right.
the universe decided to play favorites with its energy distribution.
Right. But wouldn't that mean like everything we thought we knew about the early universe
Yeah.
being uniform is wrong? I thought the Big Bang Theory suggests that the universe should look pretty much the same in all directions.
Yeah, that's the prevailing theory. Yeah. And what's even more perplexing is that this isn't like a brand new discovery.
Yeah.
Like this asymmetry was first observed back in 2003 using data from the Wilkinson Microwave Anisotropy Probe, WMAP for short.
Oh, so like scientists have known about this for over 2 decades. Why are we just hearing about this now?
Well, initially, a lot of physicists thought it might just be like a fluke in the data,
Oh.
a statistical blip that would go away as we got better measurements.
Okay.
But the anomaly persisted, and more recent data from the Planck Mission, a space observatory that provided even more detailed maps of the CMB,
Right.
actually like reconfirmed it.
Oh, wow.
So that's why it's causing such a stir in the scientific community.
So it's not going away.
It's not going away.
This like lopsided universe theory is the real deal.
Yeah, it's looking more and more likely.
Wow.
And that's why it's so exciting, because it really challenges, some very fundamental assumptions about the universe and how it evolved.
Right. Okay. I think I need a quick refresher on the CMB itself.
Sure.
Could you remind us what the CMB actually is and why it's so important to cosmologists?
Of course. So imagine the universe, moments after the Big Bang.
Okay.
Everything's incredibly hot and dense, a sea of energy. As the universe expands, it cools, and eventually that energy condenses into the first particles and atoms.
So the CMB is like the leftover heat from that initial explosion.
Exactly.
Right.
It's like a faint afterglow of that incredibly energetic event,
Yeah.
stretched out over billions of years,
Yeah.
and cooled down to about 2.7 Kelvin, which is just a few degrees above absolute zero.
Right.
It's the oldest light we can observe in the universe.
It was literally like the first light that ever existed.
Yes.
Wow. That's amazing.
It is. And what makes it even more amazing is that embedded within this seemingly uniform light are these tiny temperature variations, fluctuations that act like a map of the early universe.
Oh, wow.
By studying these fluctuations, we can learn about the conditions that existed, just moments after the Big Bang,
Yeah.
and how the universe evolved to form, the galaxies and structures we see today.
So it's like looking at a blueprint of the universe's construction plan.
In a way, yes. And within this blueprint, we found this strange asymmetry, this hemispherical power asymmetry, which doesn't quite fit with our current understanding of how things should work.
I'm starting to see why this is such a big deal. So we've got this like baby picture of the universe,
Yeah.
and one side of the picture looks way different than the other. But how do scientists even go about decoding this kind of information? We're talking about something that happened like billions of years ago.
Yeah, they do it by analyzing the power spectrum of the CMB. Imagine a graph
Okay.
where each peak and valley represents a different size scale of these temperature fluctuations. What we're seeing is that one side of this graph is much more mountainous than the other, indicating like a greater concentration of large-scale fluctuation.
Okay, I'm following so far.
Mm.
But the big question is, why is this happening?
Right.
Is there any sort of cosmic explanation for why one side of the universe would look so different?
That's the million-dollar question, and it's the reason why this anomaly is so exciting. The truth is we don't have a good explanation yet. Current cosmological models, which are based on the idea of a homogeneous and isotropic universe, just don't account for this kind of asymmetry.
So this discovery is really forcing scientists to rethink some pretty fundamental stuff. What are some of the leading theories that are being proposed to explain this like cosmic wonkiness?
Yeah, well, there are a few possibilities that scientists are exploring.
Okay.
One is that it could just be like a statistical fluke,
Uh-huh.
a random occurrence that doesn't actually reflect any underlying asymmetry in the universe.
So maybe we're just getting like a really weird snapshot of the universe, kind of like if you took a picture of a perfectly round ball and it happened to look oval from that specific angle.
Yeah, that's a good analogy. It's always possible that we're seeing like a rare event that wouldn't be representative of the universe as a whole.
Right.
But remember, we're talking about a statistical significance of between like 2 and 3 sigma,
Okay.
which means the chance of this happening randomly is pretty low.
Okay, so a cosmic coincidence is possible, but not very likely.
Right.
What are some of the other explanations?
Another possibility is what's known as observation bias.
Okay.
Could it be that like the way we're collecting or analyzing the CMB data is introducing a bias that's creating this apparent asymmetry?
That makes sense.
Right.
And we were talking about incredibly faint signals from billions of years ago.
Yeah.
Surely there's some room for error there, right?
Absolutely. It's a valid concern in any scientific field, but especially in cosmology where we're dealing with such vast distances and like mind-boggling timescales.
Yeah.
So scientists are carefully scrutinizing their methods to see if there might be any systematic errors that could account for the observed asymmetry.
So those are the less exciting explanations.
You.
A fluke or a bias in our observations.
Right.
But I have a feeling there's a more intriguing possibility out there, something that would really shake things up.
You're right. The most fascinating and potentially paradigm-shifting possibility is that the asymmetry is real and reflects something fundamental about the universe that we don't yet understand.
Now we're talking.
Yeah.
But what could that something be? What are the implications of a truly non-uniform universe?
Yeah, that's where things get really interesting and where we start venturing into the realm of speculation.
Okay.
One possibility is that it challenges the idea that our location in the universe is random.
You're not saying that we're at the center of the universe, are you?
No, no, no.
I thought we got over that a few centuries ago.
Not at all. But
Yeah.
it could mean that we occupy a region of the universe that's somehow unique. A region where physical laws or properties might be slightly different than in other regions. Imagine if the universe on a very large scale had like subtle variations.
Okay.
Almost like a cosmic tapestry with different patterns woven into it.
So instead of a perfectly smooth and uniform universe, maybe it's more like a patchwork quilt,
Yeah,
with different patches having slightly different characteristics.
that's a good way to visualize it.
Yeah.
And if that's the case, it raises some like mind-boggling questions.
Like
What caused those variations?
Yeah.
Are there other regions of the universe out there that are vastly different from our own?
Okay, this is definitely making me rethink everything I thought I knew about the universe. But let's get back to the asymmetry itself. If it's real,
Yeah.
what kind of new physics could it be hinting at?
This is where it gets really exciting for physicists. The asymmetry could potentially point to the existence of new particles or forces that we haven't even imagined yet.
Wow.
Things that played a role in shaping the universe during its earliest moments, but that we don't currently have any evidence for.
So it's like finding a hidden message encoded in the background radiation of the universe.
Exactly.
A message that hints at something we don't yet understand.
It's a clue that our current understanding of physics might be incomplete.
Right.
That there's more to the story than we currently know.
That's really thought-provoking.
Yeah.
But I think our listeners might be wondering, why should we care about this?
Yeah.
How does this asymmetry, this hidden message in the universe's baby picture, affect our day-to-day lives?
It's a fair question. On the surface, it might seem like an abstract scientific puzzle, something only cosmologists should be concerned with. But it goes deeper than that.
In what way? How does it connect to us down here on Earth?
Because ultimately it's about understanding our place in the cosmos, the fundamental nature of reality itself. If this asymmetry is real, it means there's a whole lot more to the universe than we currently understand, and that has implications for everything from the way we view the world to the very laws of physics that govern our existence.
So it's not just about what's happening billions of light years away.
No.
It's about potentially rewriting the textbooks and changing the way we understand the very fabric of reality.
That's the power of cosmology. It forces us to confront the biggest questions and to be open to the possibility that we might not have all the answers yet.
Yeah, it really is amazing to think that something as seemingly simple as like a temperature variation in the universe's first light, could have such profound implications for our understanding of like the whole cosmos.
It really highlights like the power of observation and scientific inquiry. Even something that might seem like just a minor anomaly can potentially lead to major breakthroughs in our knowledge.
So where do we go from here? What are the next steps in unraveling this whole mystery of the hemispherical power asymmetry?
Well, the key is to gather more data and refine our models. Scientists are already planning new missions and developing even more sophisticated instruments to study the CMB in even greater detail.
Like what kind of instruments are we talking about?
Well, there are proposals for new space telescopes that would be specifically designed to measure the polarization of the CMB light. And this could provide even more information about the early universe and potentially help us distinguish between different theories for the asymmetry.
That sounds incredibly complex. I can't even imagine the kind of technology that it would take to like measure the polarization of light
Yeah.
coming from billions of years ago.
Yeah, it's cutting edge stuff for sure, but that's what makes cosmology so exciting. It's pushing the boundaries of what's technologically possible and constantly challenging us to think bigger and bolder.
So it's not just about building bigger telescopes.
Right.
It's also about coming up with new ways to like analyze the data and test our theories.
Exactly. We need to be willing to challenge our assumptions and be open to new ideas, even if they seem radical at first. This anomaly is a reminder that the universe is full of surprises, and we're just scratching the surface of what's out there.
That's a great point. This is all pretty mind-boggling. But I have to admit, I'm feeling kind of inspired by the idea that there's still so much we don't know about the universe. It makes you realize that there's always more to discover.
Yeah, and who knows what we might find. The universe has a way of exceeding our expectations. The discovery of the hemispherical power asymmetry is just one example of how science is constantly evolving and revealing new mysteries for us to explore.
I'm definitely going to be keeping an eye out for more news on this. It's fascinating to think that we might be on the verge of a major shift in our understanding of the cosmos.
Yeah, and if anyone out there is feeling inspired to learn more about cosmology and the CMB, the article we discussed mentions some great resources like brilliant.org. They offer courses and interactive explorations that can help you delve deeper into these topics.
That's a great tip. Thanks for pointing that out. So folks, if you're ready to dive into the mind-blowing world of cosmology, be sure to check out brilliant.org. And in the meantime, keep looking up, keep asking questions, and never stop exploring the wonders of the universe.
Well said.
And that brings us to the end of another deep dive. We hope you enjoyed exploring the mysteries of the hemispherical power asymmetry with us. Until next time, keep those cosmic questions coming.